Hello students, in this lecture you will learn to derive the expression for the potential due to electric dipole. This slide gives you the concepts which are required to derive the expression for electric potential due to electric dipole. What you require is a binomial theorem. Here it gives the expansion of 1 minus x raised to n. N is an integer. X is a number much lesser than 1. And I have written here first terms, two terms, 1 minus nx. The sign alternates here, plus minus plus. The higher terms are not written here because they will be neglected because their value is very small as compared to 1. Then the electric potential due to a point charge, symbol is phi, equal to 1 by 4 pi epsilon 0 q by r. So r is the distance of the point from the charge q. The electric dipole consists of two equal and opposite charges separated by a small distance. Then physical quantity associated with the electric dipole is electric dipole moment, which is P equal to Q into L. L is the distance between the two charges. It is vector quantity. It is directed from minus Q to plus Q, and its SI unit is coulomb meter. Consider the diagram which is drawn here. It consists of the electric dipole, so minus Q plus Q, separated by distance L, and we have shown here vector from minus Q to plus Q. It represents vector L, which also represent the electric dipole moment. Then we are to find the electric potential at the point P. It is specified, its position is specified using the position vector, vector r. Then the position of minus q is given by position vector, vector r dash, and then by using the law of triangle of vectors, this vector plus this vector equal to this vector. This r dash plus r minus r dash equal to r. Then this is vector L. So again we use the law of triangle vector for this triangle. So this vector, which is r dash, plus this vector, which is vector L, is equal to this vector, vector r dash plus vector L. Electric potential at the point P due to this system of two charges equal and opposite, we have written phi of vector r. So this, the phi is a function of vector r because this potential is at this point whose position vector is vector r. Then this potential here is due to charge plus q and charge minus q. So we have written phi suffix plus q and phi suffix minus q. Then the charge plus q is at this distance. So this distance is this vector plus this vector. But here the vector L is in this direction. So just opposite to that is minus vector L. So minus vector L plus r minus r dash. That is the distance of the point P from the plus q. So here phi suffix plus q is a function of vector r minus vector r dash minus L. Then this phi minus q is a potential at point P due to minus q. This distance is vector r minus vector r dash. So phi minus q is a function of vector r minus vector r dash. Then we use the formula for the at a point due to the point charge. This minus q and plus q are point charge, and by in terms of vectors, we write it here as 1 upon 4 pi epsilon 0 q by vector r minus vector r dash minus vector L modulus of that, because this is a magnitude. The potential is a scalar quantity. So we take the distance of that point P from the point charge plus Q as vector r minus vector r dash minus vector L, and modulus of that, because this is a scalar quantity. Then the potential at a point P due to minus Q is 1 upon 4 pi epsilon 0. The charge is minus Q divided by, because the potential is a scalar quantity, and for scalar quantity sign has its own significance, and here charge is minus Q, so we take here minus Q, and divided by distance, this distance, modulus of vector r minus vector r dash. The next we take this Q outside, so we get a Q by 4 pi epsilon 0, and this what remains inside the bracket, and that is the equation 1. Now we have come up to this equation 1. So now we try to simplify this, the expression for the potential, by simplifying this first term 1 by modulus of vector r minus vector r dash minus vector L. So we start with that. Take it in the numerator. So power 1 becomes minus 1. Then we multiply and divide by 2. So 2 comes here, and this becomes minus half. Then we expand this, x minus y the whole square, x square minus 2xy plus y square. And similar thing we had done in the previous lecture in case of expression for the electric field due to the dipole. Then we take this out of the bracket, and what remains here is 1. Here that modulus of r minus r dash square was not there, so we divide it here. Here also it was not there, we divide it here. Then this r, the modulus of r minus r dash whole square is taken out. So when you take it out, so this, see, 2 multiplied by minus half is minus 1. So it comes out as the modulus of r minus r dash raised to minus 1. Then we write it, take it in the denominator, so it becomes 1 divided by modulus of r minus r dash. And then this what will remain inside. So next we use the binomial theorem, that 1 minus x is this term raised to n is minus half, is equal to 1 minus nx plus higher order terms are there. So we write here 1 minus x raised to n, so n comes as a multiple, so minus half comes as a multiple, into this term. This term is also there, but we are not writing it because we are going to neglect it, because it is of the power 2 here, L square, so it becomes smaller. So that's why we have not written those terms. So here we have used a binomial theorem. So we have done away with this power. Then minus minus becomes plus, and 2 cancels, so we get this term. This we have derived in the previous slide, and this is that equation 1 which was written earlier. So now we substitute this into this equation 1. So we substitute this in that first term. So we get like this. So this is written here. Then minus 1 by modulus of r minus r dash, we write it here. So the second term is written here, and this first term we use this expansion and we write it here. Then first term and the last term cancels, and what remains there is this second term plus higher order terms are there, but again they will be have the higher power, so they will become negligible. So we neglect those higher order terms. So we don't write it here because we neglect it. Then we take this q inside, so it will be q factorial. Q factorial is nothing but vector p, which is the electric dipole moment. And finally we get the expression for the potential as 1 upon 4 pi epsilon 0 vector r minus vector r dash dot vector p divided by modulus of vector r minus vector r dash cube. So in the previous slide, we have found the expression for potential at some point from the electric dipole. So now we find out if this dipole is placed in external electric field, what will be the potential energy possessed by the dipole. So we make use of the basic definition of the potential, which is work by charge. So work is equal to charge into potential, but that work done is stored as a potential energy. So we now use that. So potential energy of the dipole is the potential energy of charge minus q and potential energy of charge plus q. Then this charge is minus q and potential where the charge minus q is kept is the phi suffix external because of the external field, and that charge minus q at the position vector r dash. Similarly here, this is the potential energy of the charge plus q. So we take that charge plus q into potential at that position where charge plus q is kept is vector r dash plus vector l. So we get this equation. Then we try to expand this for a small dipole. Phi external vector r dash plus vector l. Actually, this is what is called as a Taylor's expansion. And in Taylor's expansion, we use a derivative. So here it is a three-dimensional derivative, which is del. So using the Taylor's expansion, we get phi of external r dash plus vector l dot the grad of phi external vector r dash. We substitute it here, and when you substitute here, this term, first term, and the second term cancels. So what remains behind is q vector l dot the gradient of phi external. But then q into vector l is nothing but electric dipole moment vector p. Then this is dot gradient of phi. But we already seen in the earlier part that electric field is minus gradient of potential. So we substitute this gradient of potential is equal to minus E here. So this becomes minus P and dot gradient dot electric field. So this gradient of the potential is equal to minus electric field. So we substitute here minus electric field. So what you get is potential energy, symbol is U, that is equal to minus vector P dot vector external electric field.